Alright, okay, this third problem, you look at it and 3 and 4 are not going to simplify. So is there anything you can pull out of the radical in the denominator? And you can pull out some n's. So on top, that's going to stay the same. On bottom, you're going to have 4. You're going to pull out, it's a square root, so you can pull them out in sets of 2. So there's n to the 4th, so I'm going to pull out 2 sets of them times 5m. Okay, so that's your move number 1. Move number 2, you're almost done, except for it is illegal to have this in the denominator. So you are going to multiply by that exact radical. You need to include the 5 and the m, both of them. So you're going to times the top and bottom by square root of 5m. And that's the same as timesing by 1, so you're not changing the value of anything. Okay, your top is going to be 3 times the square root of 5m. Your bottom is going to be 4n squareds times the square root of 25m squared. So now you just created a perfect square. Last step is just simplify it. Alright, so your top is not going to change. I just copy and paste. Your bottom, I've got a 4 times the n squared times anything that comes out was multiplied. Square root of 25 is a 5, and square root of m squared is just m. So my final answer is going to be 3 times the square root of 5m times, or divided by 20 n squared m. Alright, can I clean up 3 and 20? No, you're done. Next one. Okay, if you morph this guy, you're going to write your radical and 216m to the 9th. Your denominator is always the index. So it's going to be the cube root of this to the 4th. Okay, now 216. Anytime you've got a number under the radical, let's do its prime factors. So 216, I'm going to break that up. I'm going to go 4 and 54. I'm going to go 2 and 2, 9 and 6, 3 and 3, 3 and 2. Okay, so I'm going to swap out 216. I'm going to write the cube root. I'm going to trade 216 for, I think I got 3 of each. Yeah, I do. I've got 2 cubed times 3 cubed times m to the 9. But that's all in parentheses still, and there's still an exponent of 4. So, move number 3. You need to distribute this exponent of 4 to each of the 3 factors in here. And it's going to be the cube root of 2. Okay, now here's what you do with those. Do you add them, subtract them, times them, divide them? If you have 2 cubed raised to the 4th, you times them. So you're going to have 2 to the 12th, 3 to the 12th, m to the 36. Okay, let's just pull things out. You pull them out in sets of 3. So I've got, how many 2's can I pull out? How many sets of 3 are there in 12? So on the outside I can pull out 4 of them times 3 to the 4 times m to the, how many 3's are in 36? 12. So on your calculator you can go 2 to the 4th times 3 to the 4th, and you're going to end up with 1296 times m to the 12th. Final and best answer. Okay, the negative exponent on this next one. Anytime you have a positive exponent, that's repeated multiplication. But if you have a negative exponent, that is repeated division. So the trick is pretty slick. If you ever have a negative exponent, how you remedy that is you just write it over, make a fraction out of it, put it under 1. So here's my move number 1. I'm going to put 1 over 81 r to the 6th raised to the 3/2 power. That's move number 1. Move number 2, let's morph it. So let's go 81 r to the 6th. My 2 is going to be a square root, and my 3 is going to go here. Okay, let's bust up 81. That's 9 and 9. That's 3 and 3. 3 and 3. Always do prime factors of a number under a radical. So you're going to have 1 over square root of 3 to the 4th r to the 6th, but that still needs to be raised to the 3rd power. So you need to take that 3 to everything. I'm going to run out of room, so I'm going to come back up over here. So you're going to have 1 over the square root of 3 to the 12 r to the 18. Okay, now let's pull some stuff out. 1 over, how many 3's can I pull out? How many 2's are there in 12? There's going to be 6 of them. And how many r's can I pull out? How many 2's are in 18? There we go. So final and last answer. Maybe I'm going to do 3 to the 6th. So that's 729 r to the 9. Okay, I think that's good. Somewhere it feels like I made a mistake, but I think we're good. Pretty sure that's it. Okay, last one. The fraction. Let's simplify it. Let's, on top, I'm still going to have 3. And on bottom, I'm going to have 2 on the outside. So those don't simplify. Let's look at our insides. Inside, I got a 3 and a 2. Those are not going to change much, but now my x's. Okay, one of these x's on bottom is going to cancel out one on top, so on top I'm going to have x cubed. My y's, one of these y's on bottom is going to cancel out one on top, so I'm only going to have y cubed. So now on bottom I have nothing. Now, on top, let's pull some stuff out. Before we even begin, let's pull some stuff out. Let's pull some x's and y's out. So on top with my 3, I'm going to pull out, it's a square, so I can pull them out in sets of 2. How many 2's are in 3? 1, but there's 1 left over. I need to squeeze a 3 in there, because that 3 is going to stay underneath. And y's, the same thing. I've got enough, I can pull one of the y's out, but 1 stays in. So there's my top. My bottom is going to stay just like that. And it looks pretty good except for this one rule that says it's illegal to express it with a radical on the bottom. So I'm going to times the top and bottom by whatever it is that is illegal. So I'm going to times the top and bottom by square root of 2. So my top is now going to become 3xy times the square root. Since that's underneath, I can only times it with the 3 because it's underneath. So it's going to be 6xy. On bottom, on the outside, don't forget this 2. And now times your underneath. 2 times 2 is 4. Okay, now this is awesome because you just created a perfect square. What is the square root of 4? So your final answer, you're going to have 3xy times 6xy underneath the radical. And then on the bottom you're having a 2 times a 2, which is a 4. Okay. What would a number line look like if it only had the naturals? It would not look like a line at all. It would look like this. So your first natural, you'd have like a point at 1, and you would have a point at 2, you'd have a point at 3, you'd have a point at 4. But between those points there would be nothing connecting them. It would just be empty space. So it would not look like a line, it would just look like numbers. What would a number line look like if it contained integers? You would have the same points as before, a point at 1, a point at 2, a point at 3. but then you'd have some more to the left. You'd have a point at 0, you'd have a point at -1, you'd have a point at -2, but there's going to be nothing between those numbers. They're just kind of like random points in space. Okay, now the rationals is more like a line. If you had the rationals all together, you'd have between 0 and 1 now, you would have a lot of points. Between 1 and 2, now you would have a line connecting them. Between 2 and 3, now the only thing this number line would be missing, this number line has most every number that we use, but it is missing a couple. I know that pi is not rational. Pi is like 3.14159. So pi is a number, and it's between 3 and 4. So somewhere between 3 and 4, you would have a gap in your number line. So if you were driving down the road, you'd drive off a cliff. You'd hit a big pothole. Okay, and same for your other irrationals are mostly square roots. So square root of 2. Square root of 2 is actually a number. It's like 1.41 blah blah blah. So it's a number between 1 and 2, but between 1 and 2, when you came to that number, there would be a hole missing. So your number line would not quite be complete. You'd have gaps here and there, but it looks a lot better than the first two. So this last question, if it only had irrationals, it's kind of like these first two. You would have no line, because there's not a lot of irrationals. You'd have a point at square root of 2, you'd have a point at square root of 3, but you'd have nothing between them. You'd have a point at square root of 5, you'd have a point at square root of 6, so it would look more like the first two. But then when you put them all together, you have a complete number line. Alright, what is the closest natural number to 100? That is surrounded 100. The closest natural number to the left is 99, but the closest one to the right is 101. And that is actually going to be the same answer even for the integers, because naturals, wholes, integers, naturals and wholes are both integers. So same answer for 1, 2, and 3. Now what is the closest rational number to 100? So between 99 to 100, now we've got all these fractions and decimals. If you're going from 99 to 100, I want to know this number right before 100. And it's actually going to be like 99.9999. There's going to be millions of these. And the answer is there is not one. Because I can always find one smaller. Or bigger, I guess. In this case it would be bigger. So if you put 1,000,000,000,9s on here, I could put 1,000,000,001. I could always get a little bit closer, a little bit closer. And if I can keep going on forever for the rest of my life, I'll just get closer and closer to 100, but I'll never actually find the one unique number that is the closest to 100. And if you come from the other direction, if you come from 101 approaching it, same thing. You can always get close, 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 but no matter how many days and months and years you spend getting close to 100, you can always get closer. And that is the same exact answer for this guy. Okay, now square root of 24. Here's what I know. I know that 4 squared is 16. I know that 5 squared is 25. So I know the square root of 16 is 4, and I know the square root of 25 is 5. And I know that 24 is right in between these two. It's between square root of 16 and square root of 25. So on my number line, the answer to this problem is going to be somewhere between 4 and 5. Probably closer to 5. Square root of 95, same thing. I know that 9 squared is 81. I know that 10 squared is 100. So, square root of 81 is 9. Square root of 100 is 10. 95 is between 81 and 100. So on my number line, my answer is going to be between 9 and 10, somewhere in here. Okay, we're going to have time to do them all, but let's do some of these hard ones. Let's do this guy right here. 7th root of negative 65. So here's what I'm asking. What number times itself 7 times is a negative 65? Okay, you totally guess. So I'm going to try a negative 2. So negative 2 times itself 7 times. On your calculator, you've got to put the parentheses. So negative 2 to the 7th equals a negative 128. So I kind of close. So I'm going to adjust. I'm going to try a negative 1. A negative 1 to the 7th is just going to be a negative 1 times negative 1 times negative 1 over and over. So it's going to be a negative 1. Okay, now I know it's between those two integers. So a negative 65 is between a negative 128 and a negative 1. So what number times itself 7 times is going to end up at negative 65? It's going to be a number between a negative 1 and a negative 2. And it might even be like right halfway in the middle, because 65 looks like it's kind of halfway between 1 and 128. So it's going to be some number between those two suckers right there. Okay, now you for sure have got to understand this guy right here. This is an awesome question. What number times itself 8 times is a negative 29? Alright. Now, you try something. I'm going to try, I know this. I know a negative 1 times itself 8 times. Now here's the question. It's 8 times. So it's going to be a negative 1 times a negative 1. That's always a positive. And there's always going to be a pair. There's 4 of them. There's 6 of them. There's 8 of them. So I know it's going to be paired off evenly. There's not going to be any left over. So my answer is going to be a positive 1. And no matter what I choose, if I choose negative 2 to the 8th power, on my calculator, negative 2 to the 8th power, that's a positive 256. It's always going to be positive because the exponent is even. That means I have an even amount of factors. So all my negatives are going to be paired up and they're going to all turn into positives. So this is a trick question. There is no solution. I can never ever, but here's why. That's important. You're going to have to explain why on the test. I cannot times a number 8 times and end up with a negative result. No matter what number I choose, when I multiply it by itself 8 times, my result will always be positive. We're almost done. Okay, last ones from our problems of the week. What number is in the ones digit when you simplify these guys? So 4 to the 100th. Hopefully from 3 to the 100th, here's what we're after. We got to find a pattern. 4 to the 1 ends in a 4. 4 squared, that ends in 16, so that ends in a 6. 4 cubed. 4 cubed is 64. 4 to the 4th is 256. So you just need to do a handful of them. 4 to the 5th is going to be Whoops, let's see. 256 times 4. 1024. Okay, now look. You gotta find a pattern. Your pattern should jump out at you. Your last number is a 4. Your last number is a 6. Your last number is a 4. Your last number is a 6. Your last number is a 4. So it alternates 4, 6, 4, 6, 4, 6, 4. So your ones digit, no matter how many times you multiply, is either going to be one of two things, a 4 or a 6. So if I multiply 100 times, the question is, does it end up on 4 or does it end up on 6? And the answer is, it ends up on 6. Because every even power ends up on 6 and every odd power ends up on 4. 100 is even. So you're in good shape. Let's maybe do one more. Let's do this guy right here. Let's do 8 to the 32nd. That's going to be a little different. Okay, same thing. Let's find the pattern. 8 to the 1 is 8. 8 squared is 64. 8 cubed is 512. No pattern yet. 8 to the 4th is 2040. Let's see, did I mess up somewhere? 2048. So am I on to something? Let me check real quick. 8 to the 1 is 8. 8 squared is 64. 8 cubed is 512. 8 to the 4th. Oh, I did mess up. 8 to the 4th is not 2048. 8 to the 4th is 4096. Alright. 8 to the 5th is 32768. Now I think I'm on a pattern. It looks like it's going to go 8, 4, 2, 6, 8. I'll bet the next one's 4. 8 to the 6th does end up. It's 2, 6, 2, 1, 4, 4. So check it out. Here's my pattern. It's going to be 8, 4, 2, 6. So 8 to the 1 is going to end in 8. 8 squared ends in 4. 8 cubed ends in 2. 8 to the 4th, and it's going to repeat. So 8 to the 5th, 6th, 7th. 8 to the 8th ends in 6. 8 to the 9 ends in 8. 8 to the 10 ends in 4. 8 to the 11 ends in 2. 8 to the 12 ends in 6. It's going to cycle through this pattern. 8 to the 13, 14, 15, 16. So if I need to end up at 32, I can just keep counting. 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So 8 to the 32 ends in a 6. But if it was a large number like 2,000, you wouldn't want to count. So here's how you do it. I know one complete cycle contains 4 digits. So here's what I want to know. I'm going to do it 32 times. How many times is my cycle going to go through? So 32 divided by 4, because a cycle contains 4 digits. 32 divided by 4, that's actually a perfect whole number, 8. It's going to cycle through 8 times. And on the 8th time, it's going to end complete. And it's going to end up right here on the very last digit, 6. So 33 would be this. If you do 33 divided by 4, 33 divided by 4 is 8.25, or it's 8 1/4. So it would cycle through 8 times, and then 1/4 would be your first of the 4 digits. So 8 to the 33 is going to end in an 8.